Good evening, everyone. In the last lecture, we had a discussion over the different AC circuits. We discussed the LCR circuit in the last time, right? We also discussed the different aspects of the AC circuits. We discussed about the impedance, that's the total resistance, right, offered by the circuit, right? And we also discussed about the phase difference between the current and the voltage as well. And we also discussed about the voltages across the voltage and the current across the different electrical AC elements, right? But today in this lecture, we'll be starting with some of the questions related to AC circuits, and then later in this lecture, we'll be discussing about the resonance and the quality factor of a circuit, right? So let's begin with this question, right? On the screen, you can see that for the given LCR series circuit, right? Find out the applied source voltage of AC, right? We have to find out the applied source of the voltage of AC, right? So since all the three elements here, resistor, inductor, as well as capacitor, all the three elements in a circuit are in series, right? If all the three elements in this circuit are in series, it means that the same current will be flowing through them, right? Same current will be flowing through them, right? But we do not know the source of the voltage, right? How much voltage is being supplied at this instant, right? At this instant to each of these electrical elements, right? But we know that if we draw the phasor diagram, right? If we draw the phasor diagram for all these electrical elements, right? For all these electrical elements, with the help of phasor diagram, we can easily find out the what we call as the source voltage, right? You know that if this is the current, right, I, and we know that the phase difference between the current I and the voltage across the resistor is zero. It means that the current through the resistor and the voltage through the across the resistor are in phase. It means that if this is the direction of the current I, then same will be the direction of this voltage across resistor. That's VR. And we also know that in case of inductor, in case of inductor, the voltage across the inductor is actually leading by 90-degree with respect to the current, right? So it means that if this is a zero line, then this will be the 90-degree, right? This will be the 90-degree. Then it means that this will be the direction of this VL phasor, right? This will be the direction of this voltage. And similarly, in case of capacitor, the voltage is actually lagging behind the current, and it is there's a phase difference of 90-degree between the current and the voltage. In case of capacitor, current is leading in case of capacitor by a 90-degree. It means that if this is the sense of the current, then this has to be the sense of voltage across the capacitor, right? Voltage across the capacitor. It means that we treat these phases of voltage and current as vectors, right? We'll be adding all these voltages and current as like we do in vectors, right? We can see here VL and VC here are opposite in direction, right? So the net resultant of VL and VC will be along this direction because VL is greater than VC. So this will be VL minus VC, right? This will be VL minus VC. And this is R, right? This is R. The resultant of VL minus VC and R will be along this direction, right? It will be along this direction. And this will be the resultant of the voltage supply, right? This will be the voltage supply, right? This will be the resultant voltage supply at this instant. Or we can say the resultant voltage supply here, V, will be equal to under root of VL minus VC whole square plus VR square, right? VL minus VC whole square plus VR square. We know the value of VC, we know the value of VL, we know the value of VR, right? We can just plug in the values of VL, VC, VR in this equation to get the voltage supply by the source, right? To get the voltage supply by the source. The voltage supply by the source will be equal to under root of VL, that's given as 50. It will be 50 minus VC, that's equal to 20, right? Whole square plus VR square, that's 40 square, right? So it will be 30 square. 30 square will be 900, right? It will be 900. And 40 square will be 1600, right? 1600. And if we add it, it will be 2500, root of 2500. And root of 2500 is nothing. It's actually 50 square. That's 50, right? So 50 volt is actually the net voltage supply, right? Net voltage supply by the source. You can see here, actually, you can see here the net voltage supplied by the source is actually only 50 volts. But in case of AC circuits, right? In case of AC circuit, the individual voltage actually can exceed the source voltage, right? They exceed the source voltage. But in case of DC currents, if the elements are in series, the total voltage cannot exceed the source voltage, right? But in case of AC, it is possible, right? The total voltage, the sum of the individual voltages can actually exceed the source voltage, right? You can see that here clearly, right? So the source voltage here comes out to be equal to 50 volts, right? Now let's find out the impedance of the given circuit. The question says that we have to find out the impedance of the given circuit, right? It's a series LCR circuit, right? We have 4 ohm resistor, 9 ohm inductor, right? 6 ohm is the resistance offered by the capacitor, right? There must be some AC source here, right? AC supply. Let's suppose that the AC supply here is V, right? Now we have to find the effective resistance, right? Now the resistance offered by this series LCR circuit, right? Series LCR circuit, that's what we call as the impedance of the circuit, right? The net resistance offered by the circuit, that's what we call as the impedance of the circuit, right? In case of series LCR, right? Now, once again, we'll be using the concept of the phases, right? Concept of the phases. In the previous lectures, we also saw that the net resistance of series LCR circuit is given by XL minus XC whole square plus R square, right? This was the net resistance or the net impedance offered by the series LCR circuit, right? Where XL is nothing. XL is the impedance of reactance offered by this inductor, that's equal to omega L, right? Omega L, and XC is the resistance offered by the capacitors, that is 1 over omega C, right? And R is the resistance offered by the resistor, right? Now, uh, in this question, we can see that we have not given any frequency here, right? The value of frequency is not given here, right? So, but we have to find the net impedance here, right? Net impedance. So net impedance XL is given here. XL has been given as how much is the value of XL? That's the 9 ohm, right? It's directly given as 9 ohm. And XC is given directly as 6 ohm, right? It's directly given as 6 ohm. And the value of resistance R is given as 4 ohm, right? 4 ohm. We can just directly plug in the values of XL, XC, and R in this equation to calculate the impedance offered by the circuit, right? So the impedance offered by this circuit will be under root of XL minus XC. XL is 9 minus XC, that's 6 whole square plus 4 square, right? So it will be equal to 3 square plus 4 square, right? That will be equal to under root of 25, right? And root of 25 is nothing, that's equal to 5 ohms, right? So the net impedance offered by this circuit is nothing, that's equal to 5 ohms, right? So that's the net impedance. In case of series DC current circuits, right? DC current circuits, right? DC circuits. The net impedance is actually the sum of each and every resistor in series, right? Right. So, but in case of AC circuits, we add the resistances are not added as in case of DC currents. The addition of the resistance is different as compared to the addition of resistance in DC currents, right? You can see that clearly, right? So this is the 5 ohm is the answer for this given circuit, right? Let's move on to the next question, very important question, right? Find out reading of AC ammeter, right? We have to find out the reading of the AC ammeter, right? And also calculate the potential difference across resistance and capacitor, right? So we have to find out the reading of this AC, what we call as reading of this AC ammeter, right? Let's suppose reading of this AC ammeter at any instant is I. If I current is flowing through the circuit, then this I current will be measured by this AC ammeter. So this will be the reading of this AC ammeter, right? Now let's try to solve this question, right? Let's try to solve this question. This current I will be nothing. This current I measured by this AC ammeter will be nothing. It will be the net source impedance, right? Source voltage upon the net resistance, that is the Z or impedance, right? We know that Z is nothing, it's impedance of this circuit, and this impedance is nothing, it's equal to under root of here. And now here in this case, it will be XL minus XC ka whole square, right? Plus R square, right? Plus R square. This will be the net impedance or the net resistance offered by this LCR circuit to the source voltage, right? Or the source current, right? And the value of E is given as here, that's 100 sine of omega t, right? sine of omega t, right? Okay, it's 100 sine of omega t, 100 pi t, right? So it has to be of the form of it has to be actually 100 sine of 100 pi t, right? 100 pi t, right? There's a error in this question, right? So it's not actually omega t. It's actually 100 sine of 100 pi t. This is the supply, right? This much of supply is there, right? This much of supply is there. So current will be E upon the Z, right? Now, first of all, we'll calculate the value of Z. The value of Z will be under root of XL minus XC square. XL is given here as 20 ohm and XC is given as 10 ohm and R is given as 10, right? So it will be square here, right? So 10 square plus 10 square, it will be actually 10 root 2 ohm, right? 10 root 2 ohm. So this will be the net impedance offered by this circuit to the source current, right? Now calculating the current will be nothing. It will be 100 sine of, right? Sine of 100 pi t, right? Pi t upon uh, 10 root 2, right? 10 root 2. So this will be the current, or it will be equal to 10 upon root 2 sine of 100 pi t. So this will be the instant current measured by this source voltage, right? Source voltage, or we can rewrite it as equal to 5 root 2, right? 5 root 2 sine of 100 pi t, right? Sine of 100 pi t, correct? So this will be the current, right? This will be the current. Now we have to find out the maximum current that it can measure is the 5 root 2 ampere, right? So I max current it can measure is I max maximum current it can measure is 5 root 2 ampere, right? 5 root 2 ampere. This will be the maximum current, right? Now we have to calculate the potential difference across resistor and capacitor. Potential difference across this resistor will be nothing. It will be the current I, right? So the potential difference across VR will be nothing. Instantaneous potential difference, that will be VR. That will be the resistance R multiplied by the current I, right? A resistance R multiplied by the current I. Now R is the resistance, that's 10, and the current is 5 root 2 sine of 100 pi t, right? Sine of 100 pi t. So this will be the voltage across the resistor, or we can say that the maximum voltage across the resistor, right? Across the resistor, the maximum voltage will be 50 root 2 volts, right? 50 root 2 volts, right? And similarly, the maximum voltage across inductor will be the maximum voltage value of the voltage across the inductor will be, so it has to be equal to resistance of the inductor multiplied with the maximum value of the current. That will be 20 multiplied by 4 root 20 multiplied by 5 root 2, right? That will be XL multiplied by the current I. That will be equal to 20, right? Multiplied by 5 root 2, right? Or we can say it will be 100 root 2 volts, right? 100 root 2 volts, right? And similarly, the maximum voltage across the capacitor will be XC multiplied by the current I, right? That will be equal to XC is 10 and the maximum value of current is 5 root 2, right? We can write it equal to 50 root 2, right? 50 root 2 volts. This will be the maximum voltage across the capacitor, inductor, and the resistor, right? And we have also calculated the instantaneous current through the circuit, right? Now, let's try to solve this question as well. In LCR circuit, within AC source of resistance R equal to 300 ohms, capacitance of capacitors given as 20 microfarads, right? And the inductance of an inductor is given as 1 Henry, right? And the RMS value is given here as 50 volt, right? And the frequency of the source voltage or the source current is nothing. It's 50 upon pi hertz, right? 50 upon pi hertz. So this is the frequency, right? We have to find the RMS value of the current, right? We know that VRMS is actually equal to, for a LCR circuit, it's IRMS multiplied by the Z, and Z is nothing. This is the impedance, right? This is the impedance of a circuit, right? Impedance. And we know in case of LCR circuit, the impedance Z has the value under root of XL minus XC whole square plus R square, right? Plus R square. Now we have to calculate the value of XL, XC, and R square, right? The value of XL is nothing, that's omega L, right? Omega L. Now we can calculate it as 2 pi frequency times L, right? That will be equal to 2 pi frequencies given here. That's 50 upon pi, right? And the value of L that's given as 1, right? So it will be equal to 50 into 2 is 100. So 100 ohm is the resistance offered by the 100 ohm is the resistance offered by the inductor, right? Similarly, if we calculate the resistance offered by the capacitor, that will be 1 upon omega c, right? 1 upon omega c. Now we can write this omega once again 2 pi f into c, right? 2 pi f into c, so it will be 2 pi f, frequency is 50 upon pi, right? 50 upon pi, and the capacitance of a capacitor is given as 20 microfarad, right? So we can write it as 20 into 10 to the power minus 6 farads, right? This pi and pi will go, right? So it will be 5 to into, it will be 10, right? It will be 100, or we can write it will be 2000 here, right? It will be 2000 here. So it will be 1 upon uh, 2 into 10 to the power 3 into 10 to the power minus 6, right? Or we can write it as 1000 upon 2, right? 1000 upon 2, that's equal to 500 ohms. So the resistance offered by the capacitor here is 500 ohms, right? We got the value of XL, we got the value of XC, right? We know the value of R, that's given as 300. Now let's substitute the value of XL, XC, and R in this equation to calculate the value of Z. We will get the value of Z as under root of XL is 100, 100 minus 500, right? Whole square plus resistance, that is equal to 300, right? 300 whole square, right? So it will be equal to under root of 400 square, right? 400 square plus 300 square, right? 300 square, right? So 300 square will be actually equal to 300 square. We can write it as, so what we can do is we can write it as 400, but that will be 16, right? 16, and this it will be 16,000, right? 16,000, right? So this will be the 16,000, right? 400 square, right? So it will be 4 square. Okay, it will be 1600, right? 0000, right? Plus 90000, right? So this will be the what we call as the value of this, right? So we can write it as this value of Z, effective value of Z here, right? Effective value of Z. So it will be 300 square, 400 square, or it will be nothing. The effective resistance of the circuit will be 400 square plus 300 square. So it will be 250,000, right? Or we can write it equal to, uh, it will be equal to under root of 500 square, right? Under root of 500 square. That will be equal to 500, right? The effective resistance for this circuit is actually 500, right? Effective resistance for this circuit is actually 500. So we got the value of Z here, that's equal to 500, right? Value of Z here, that's equal to 500, right? So value of Z here is nothing, that's equal to 500 here. We can directly write here value of Z equal to 500, right, in this equation. So Z equal to 500 ohms, right? This is the effective resistance or effective value of Z. We have to calculate the value of VRMS, right? Sorry, IRMS. So IRMS will be nothing. It will be, IRMS will be equal to VRMS upon Z, right? VRMS upon Z. And the value of Z is 500, and VRMS given is given here, right? 50 volts, right? 50 volts upon 500, right? 500. So it will be nothing. It will be equal to 1 upon 10, right? 1 upon 10. That will be equal to 0.1 ampere. So this will be the value of IRMS for this circuit. So 0.1 ampere will be the IRMS value for this given question, right? Now let's discuss about the different conditions, right? Different conditions of a series LCR circuit, right? Series LCR circuit. We know that in case of series LCR circuit, we have three electrical elements, right? We have three electrical elements in case of series LCR circuit. In case of series LCR circuit, we have three electrical elements. One is the resistor, right? One is the resistor. Another is the inductor, right? Another is the inductor here. It's the inductor. And the third one is the capacitor, right? Third one here is the capacitor. So third one is the capacitor here, right? Let's suppose this is the capacitor, right? This is the resistance R and inductance L and the capacitance C, right? They are connected with some AC voltage, right? Let's suppose this is the AC source here, right? And this is our circuit. This is our circuit, LCR circuit, series LCR circuit. There will be some current I flowing through it. It will be a same current for R, L, and C. Now, what is the condition of resonance, right? What is the condition of resonance? So at resonance, what happens is that the resistance or the impedance of this circuit becomes minimum, right? The impedance of the circuit becomes minimum and the maximum amount of current actually flows, right? Maximum amount of current is flows through circuit, right? Maximum amount of current flows through circuit. So at resonance, at resonance, the inductance, the resistance or the impedance of this circuit becomes minimum, right? Impedance becomes minimum, right? Z becomes minimum at resonance, right? It's a condition at which the for this circuit the impedance becomes minimum and the current becomes maximum, right? Maximum current flows through it, right? Current maximizes, right? Current maximizes, and this condition of resonance can be attained at a particular frequency, right? At the particular frequency of a source voltage, right? And that frequency of the source voltage we call as resonance frequency. We call as resonance frequency. So the resonance frequency is the frequency at which the series LCR circuit has the minimum impedance and the maximum current flows through it. Maximum amount of current flows through it. Now let's try to see how we can actually minimize the resistance of a circuit. What is the condition to minimize the resistance of a, or the impedance of a circuit, right? So we can see that we know that the value of Z in general for the LCR series LCR circuit is XL minus XC, right? Whole square plus R square. So this is the uh, general value of what we call as impedance of a series LCR circuit, right? In series LCR circuit, what we can change actually, we know that XL depends upon the frequency, that's omega L, right? And XC depends upon the frequency as well, that's 1 upon omega C. The only thing we can change to change the resistance is by changing the frequency of the AC source, right? If we change the frequency of AC source, we can change the resistance, right? We can change the inductance of, we can change the reactance of the inductor, we can change the reactance of the capacitor, right? So that can be done only by changing the frequency of the source voltage, because in the reactance of the inductor and the reactance of the capacitor depends upon the frequency of the AC source. So what we can do is that you can see here XL minus XC. It means that XL minus XC means X is subtracted from XL. So we have to minimize Z. To minimize Z, we have to minimize this value, right? We have to minimize this value XL minus XC whole square. We have to minimize this value, right? We cannot change R because R is frequency independent, right? It's frequency independent. So upon changing frequency, the value of R remains fixed, right? Value of R remains fixed. So by changing the frequency, we cannot change the resistance. So the resistance of the resistor is a fixed quantity, right? We cannot change it by changing the frequency of the AC source. But we can change the frequency. We can change the reactance of the inductor. We can change the reactance of the capacitor by changing its frequency. So what minimum value we can get for XL minus XC? We can think that the minimum value we can get is 0. We should get a minimum value of XL minus XC 0, right? XL minus XC 0, so that the Z gets minimized. So it means that the condition for the resonance is Z should be minimum, right? For Z to be minimum, XL minus XC value should go to 0, right? This should vanish, right? This should vanish. If this value vanishes, then XL has to be equal to XC, right? XL has to be equal to XC. From this condition, we can write it will be omega L upon 1 upon omega C, right? Omega C. Now from here, you can see here omega square is equal to 1 upon LC, right? Now this omega is what we call as the resonance frequency. So this omega is equal to 1 upon root of LC, right? Root of LC. This is what we call as the condition for this circuit to be at resonance, so that the current is maximum flowing through this circuit and the impedance offered by the circuit is minimum. So at this condition, this omega will be called as resonant frequency, right? So it will be angular frequency here 1 upon root of LC, right? This is what we call as resonant frequency. This is what we call as the resonant frequency, right? Resonant frequency. At this frequency, the circuit will have the maximum current flowing through it. So you can see here the resonant frequency actually depends upon the L and C factor only here, right? Or we can write the frequency here as 1 upon 2 pi under root of LC, right? 1 upon 2 pi under root of LC. So this is our resonant frequency. We call it in short as RF, right? If this is the resonant frequency, right? If this is the resonant frequency for the condition XL minus XC is 0. If XL minus XC is 0, we get the value of Z. We get the value of Z equal to R, right? Value of Z equal to R. So minimum value of so the minimum resistance or the impedance for this circuit is equal to R. It means that we can say that at resonance, the series LCR circuit behaves as a pure resistive circuit. At resonance, the series LCR circuit behaves as a pure resistive circuit, right? So at resonance, it will behave like a pure resistive circuit, and the impedance for the circuit will be minimum. That will be equal to resistance of a resistor. And in this case, if XC is equal to XC is equal to XL, right? If XC is equal to XL and the current flowing through the circuit is same, then if resistance offered by the inductor and the capacitor is same, then it means the potential difference or the voltage across the capacitor and the resistor will also be same, because resistance is same, current is same, voltage has to be same. So VL equal to VC will, this condition will also be followed for the series LCR circuit. And one more important point, we know that this circuit behaves as a pure resistive circuit, right? And we know that for a pure resistive circuit, the phase difference between the current and voltage is zero, right? They are in phase. So this condition will also be followed here, right? This condition will also be followed here. So the phase difference between the voltage and the current in case of pure resistive circuit is zero. They are in phase. For the in the same way for the series LCR circuit at resonance, it will be a pure resistive circuit. So the voltage and current will be in phase, right? Or phase difference between them will be equal to zero, right? So these are some of the points related to the resonance condition. What is the resonance, right? What is the current at resonance, right? What is the condition for the resistance, and what is resonance frequency? And we can see that resonance frequency is it's independent of the resistance of a resistor. It only depends upon the inductance value of the inductor and the capacitance value of the capacitor, right? You can see clearly from this equation, right? Now let's we know that in case of series LCR circuit, if we plot a graph between the current versus the frequency, right? We know that the current is dependent on the frequency, right? If we plot the graph between the current and the frequency, right? Current and the frequency, you can see that for different fixed frequencies, we have different values of the current, right? We have the different values of current, but you can see there is a peak of this current, right? There is a peak of this current through the circuit. This is the maximum value of the current that can flow through the circuit. And the maximum value of current that can flow through the circuit is only possible at the resonance frequency, right? At the resonance frequency. So this is the value of the frequency here, right? Let me call this frequency as F naught. This is what we call as a resonant frequency, and its values 1 upon 2 pi under root of LC. So this is the point where the resonance actually takes place, right? And at this value, the power consumption is maximum, or we can say the current flowing through the circuit is maximum, right? So this is how we can plot the how we can show the point of resonance on this current versus frequency graph, right? Current versus frequency graph, right? So now here there are two frequencies, F1 and F2, right? This is the value of the frequencies. This is the value of the frequencies, right? These are the values of the frequency at which the power consumption is half the maximum, right? Here the power consumption is maximum, right? Power consumption is maximum. Now at these points, the power consumption is half the maximum, right? It's half of the maximum, right? At these points, the power consumption is half the maximum, right? It's half the maximum. So at frequency F1 and F2, right? At frequency F1 and F2, the power consumption by the circuit is actually half the maximum frequency, right? It's half the maximum frequency, right? And and this is what we call as bandwidth, right? This is what we call as bandwidth. So f2 minus f1 is nothing. This is what we call as bandwidth, right? This is what we call as bandwidth. So this is the bandwidth for this circuit, right? This is what we call as bandwidth, right? So this is the plot between the current and the frequency of this series LCR circuit, right? And the interpretation for different points here, right? So let's try to solve this question here. A very simple question, basic question. For what frequency the voltage across the resistance R will be maximum, right? So it will be at resonance frequency. We know that at resonance frequency, the series LCR circuit behaves as a pure resistive circuit, right? And when it behaves as a pure resistive circuit, so the uh, it will be have a maximum voltage across it, right? And we have to find that frequency, right? It will be a resonance frequency, right? Resonance frequency will be nothing. That's omega naught is equal to 1 upon LC, right? Omega naught will be equal to 1 upon root of LC, right? Or we can write the frequency value here is 1 upon 2 pi under root of LC, right? 1 upon 2 pi under root of LC. So this will be the value of the frequency. Now let's substitute the values of L and C in this equation, right? The value of L is 1 upon pi microfarads, 1 upon pi Henry, right? So we can write here 1 upon pi, and the value of what we call as capacitor is 1 upon pi microfarad, right? It will be 10 to the power minus 6, right? So you can see here this pi and this pi will get cancelled, right? It will be equal to 10 to the power minus 3, right? It will be 2 into 10 to the power minus 3, right? Or we can write it as 1000 upon 2, that will be 500, right? So the resonance frequency will be here equal to 500 hertz, right? So this is the frequency, right? This is the frequency at which the resonance will take place for this given circuit, right? And it will be independent of the resistance of a resistor, right? Now let's discuss a very important concept, what we call as power factor, right? Let's discuss a very important concept, what we call as power factor of a circuit, right? So we'll be discussing the half power frequency, right? Half power frequency and the quality factor for the same circuit, for the same series LCR circuit, right? So you can see here, there are two frequencies of applied AC source in LCR series circuit, where power consumption is exactly half of the maximum at resonance. We know that power consumption is maximum at resonance. This is the frequency. This is the frequency, right? Let me call this frequency as F naught. Let me call this frequency as F1, and let me call this as frequency as F2. And this frequency, what we call as resonance frequency, right? This is the resonance frequency, right? And at this frequency, the power consumption is maximum, right? Power consumption is maximum, right? Power consumption is maximum. At this frequency, the power consumption is maximum. So at this frequency, power consumption is maximum, right? Right. Now, half power frequencies are the frequencies at which the power consumption is half of the maximum, right? At which the power consumption is half of the maximum. Means power consumption here will be P max upon 2. Now, at this point also, the power consumption here will be P max upon 2, right? P max upon 2. So this will be the power consumption here, right? This will be the power consumption. Let's suppose from here to here, if the frequency changes delta f, from here to here, frequency changes delta f again, right? Then we can write the bandwidth as 2s delta f, right? Bandwidth will be here equal to bandwidth here will be equal to 2s delta f, right? This will be 2s delta f, right? This will be 2s delta f. If this is the bandwidth, right, then we can write f1 frequency as f naught minus delta f, right? Right, or we can write f2 as f naught plus delta f, right? F naught plus delta f, correct? The value of this frequency, resonant frequency, will always be equal to under root of these product of half power frequencies, right? Or we can say the value of angular frequency will be product of omega 1 multiplied by omega 2, right? Omega 1 multiplied by omega 2. What are these omega 1, omega 2? Omega 1 is nothing, it's 2 pi f1, right? And omega 2 is nothing, it's 2 pi f2, right? 2 pi, right? So, or we can say bandwidth can be also said that it's nothing, it's 2s delta omega. It's 2s delta omega, right? It's 2s delta omega. That will be equal to 2s 2 pi times delta f, right? 2 pi times delta f, right? So this will be the bandwidth, right? So this resonant frequency is given by under root of f1 into f2, or omega naught is equal to this is angular resonant frequency under root of omega 1 to omega 2, right? Now, what we have to show is that we have to calculate this half power frequency, right? Half power frequency, right? The current at which the power will be half of the current at which the power consumption will be half of the maximum, right? Half of the maximum. So let's suppose there is power consumption P and it's half of the maximum. That's P max upon P max upon 2, right? P max upon 2, right? Now, at this point, the current will be power consumption will be I square. Let me call is half current I square multiplied by the what we call as Z, right? Multiplied by the Z, right? Multiplied by the Z. And P max is nothing. P max is actually P value of P max is this is equal to V upon R, right? Because we know that at maximum power consumption will be at resonance frequency, and at resonance frequency it behaves a pure resistive circuit, right? It behaves as a pure resistive circuit. So it will be equal to V upon R, right? V upon 2R, right? So this will be the value of what we call as what we call as this is the value of at resonance, right? This is the value of maximum value of the current. So V upon R is nothing. V upon R is nothing. It's I max, right? It's I max. It's I max, right? It's I max. Or we can write if this is the value of I max, right? If this is the value of I max, correct? If this is the value of I max, we can write the value of half frequency will be equal to. We can write it here I max upon 2, right? I max upon 2. I max upon 2, right? It will be I max upon 2. Then the value of half current here will be equal to under root of it will be equal to the value of I max will be equal to half of max current will be equal to under root of I max upon under root of 2, right? So it will be 1 by root 2 times of the maximum current, right? And the value of the maximum current is nothing. It will be the voltage, maximum voltage, right? Upon the resistance, because at resonance it will behave like a pure resistive circuit, right? At resonance, right? So it will behave as a pure resistive circuit at at this condition, right? So this will be the maximum current, right? This will be the maximum current, right? Now the question is that what is the value of this bandwidth, right? What is the value of this bandwidth, right? Delta omega, right? The value of the bandwidth comes out to be equal to the value of this bandwidth is nothing, right? Value of this bandwidth is nothing. That's equal to delta omega, right? Delta omega. That's equal to R upon 2L, right? R upon 2L, right? So this is nothing. This is the bandwidth. This is bandwidth for the circuit. Bandwidth of LCR circuit. So this will be the bandwidth of LCR circuit, right? So this will be the bandwidth of LCR circuit. So in this case, you can see that if delta omega is the bandwidth of the LCR, bandwidth of this LCR circuit, we define the concept what we call as the quality factor, right? Quality factor. The quality concept of the quality factor is that at the quality factor, the resonance, it actually signifies that how sharp is the resonance, right? How sharp is the resonance. It's not always like that it at a particular frequency the resonance will always take place, right? That's the ideal situation. There is always a quality factor that actually decides how sharp actually, how sharp the resonance is, right? How sharp actually the resonance is. It means that let's suppose we are plotting the graph between current and the frequency, right? Current and the frequency, right? Current and the frequency, right? Now let's suppose that this is the graph for the what we call as current and the frequency. You can see here there can be n number of frequencies around this point, right? Many frequencies, right? So we can say here it's not that much sharp, right? It's not that much sharp. But let's suppose if we plot this current versus frequency and we get the value like this, graph like this, right? So it's very sharp, right? It's very sharp as compared to this graph, right? So we can say here the quality of this the quality factor of this circuit is greater if this is Q2, if this is Q1, that's the quality factor. Then here you can see the resonance here is very sharp, right? The resonance here is very sharp, but here the resonance is not much sharp, right? Or we can say here the sharpness of 2 is greater than the sharpness of first, right? Is greater than the sharpness of first, right? Right? Or we can say quality factor of 2 is greater than the quality factor of 1, right? Quality factor of 1, right? So we can calculate this quality factor, right? It's defined as it's 2 pi times amount of energy stored per cycle, right? Amount of energy stored per cycle, stored per cycle upon energy loss per cycle, right? Energy loss per cycle, lost per second, energy lost per second, right? Now this quality factor Q, right? It's nothing. It's equal to this quality factor Q is nothing. It's equal to 2 times delta of omega, right? 2 times delta of omega. We know that delta omega is nothing. That has the value. The value of delta omega is R upon 2L, right? R upon 2L, R upon 2L, right? That's R upon 2L, correct? That's R upon 2L. Or we can write this the value of this what we call as R upon 2L here, that's equal to the value of R of 2 times delta omega will be equal to R upon L, right? That will be equal to R upon L, right? So it will be actually equal to uh, omega naught upon 2 times delta, right? Omega naught will be the frequency, right? Omega naught upon the bandwidth, right? It is the frequency, resonant frequency upon the bandwidth, right? Resonant frequency upon the bandwidth. You can see here there's a frequency in the numerator and frequency in the denominator. So it's actually a unitless quantity, right? Unitless quantity, right? It does not have any units, right? So quality factor is actually a unitless quantity, right? Physical quantity. It does not have any units. So Q value is nothing. Q is equal to omega naught upon 2i's delta omega, right? And the value of 2i's delta omega is R upon L, right? We can write it as omega naught uh, R upon L, right? Or it will be equal to omega naught L upon R. It's a very important equation, right? It's a very important equation, right? To calculate the quality factor of this series LCR circuit, right? So this quality factor gives an idea about the sharpness of the resistance, right? Sharpness of the resistance, right? So omega naught is nothing. Omega naught is the angular resonant frequency, right? Angular resonant frequency, right? Or we can write this omega naught equal to 2 pi times f naught, right? F naught. F naught is nothing. F naught is nothing. It's the resonance frequency, right? Resonance frequency. And we know that omega naught is nothing. That's equal to 1 upon root of LC. 1 upon root of LC. Now substituting the value of omega naught in this equation, we'll get the value of quality factor Q, that's equal to uh, L upon R, right? L upon R under root of LC, right? Under root of LC, correct? Or we can write it equal to, can write it equal to, we can write it equal to under root of L upon C, right? Under root of L upon C, right? 1 upon R, right? 1 upon R. So this will be the what we call as the condition of the resonant frequency. Sorry, quality factor, right? This will be the equation for the quality factor. So quality factor has two equations. One we call as Q is equal to omega naught L upon R, right? Omega naught L upon R. And another equation is 1 upon R under root of L upon C, right? So this equation, both these equations we can use to calculate the quality factor of a given series LCR circuit, right? So this is the quality factor, right? So both these equations we can use to calculate the quality factor of a given circuit, right? Now let's discuss about the power of a AC circuit, right? Power of AC circuit is nothing, right? If we talk about the instantaneous power, right? Instantaneous power will be nothing. It will be V by V into I, right? Let's suppose V is equal to V naught sine of omega t, right? Sine of omega t, correct? So let's suppose the current flowing through the circuit is I naught sine of omega t plus phi, right? Sine of omega t plus phi, omega t plus phi. Then the instantaneous power through the AC circuit will be equal to V into I. That will be V naught sine of omega t, right? Into I naught sine of omega t plus phi, right? Sine of omega t plus phi, correct? So this will be the instantaneous power, right? Now talking about the what we call as the average power, right? P average of a P average, right? Average power. If we just integrate this quantity here, right, between the limits, right, we can integrate it V naught sine of omega t, right, I naught sine of omega t plus phi, right, with respect to time dt, right, dt, with the limit 0 to t, right, upon integral of 0 to t dt. So this will be nothing. This will give us the average power, right? This is the P average, right? And the value of this P average comes out to be equal to, it's nothing. It's the VRMS into IRMS multiplied with the cos phi, right? So P average is nothing. P average of a circuit is nothing. It's VRMS, right? VRMS into IRMS multiplied with the cos phi. Now this cos phi is nothing. This is what we call as the power factor, right? Cos phi is nothing. It's equal to the power factor, right? It's a power factor. Power factor. What does this power factor tell us? It's actually the phi. Phi is the phase difference, right? It's the phase difference between V and I, right? Between V and I, right? So this cos of phi we call as a power factor, right? So this is a very important factor, right? This actually tells us about how much average power consumption is in different circuits, right? Let's suppose if we talk about the pure capacitor circuit, right? If we talk about the pure capacitor circuit, right? In case of pure capacitor circuit, this is the pure capacitor circuit. This is the supply, right? That's been I naught over root 2, right? This is the value of the IRMS, right? Now, cos of phi, right? And we know that in case of pure capacitive circuit, the phase difference between the current and the voltage is 90 degrees. So it will be cos 90. And we know cos 90 is 0. Or we can say the average power consumption by the capacitor in an AC circuit is actually 0, right? On an average, there is no power consumption at all by the capacitor, no power consumption at all by the capacitor, right? In a complete circuit, right? So average power consumption by the capacitor in an AC circuit or AC source is actually equal to 0. And same goes with the inductor as well. For inductor also, cos of pi is actually equal to cos of 90 degree, right? Cos of 90 degree. So for this also, P average will be equal to 0, right? So it means for both capacitor and inductor, the average power consumption equal to 0, right? For both capacitor and inductor average power consumption is actually equal to 0, right? So only active element here is that's the what we call as pure resistor, right? Pure resistor. Let's suppose this is the pure resistor, right? And we are supplying some AC to this resistor, right? To this resistor, right? And there is some current flowing through this resistor, right? I. And we know that for pure resistor, once again, the P average will be nothing. It's VRMS, right? Upon VRMS multiplied by IRMS, right? Multiplied by the power factor, that's cos of phi, right? Cos of phi. Now you know that in case of pure resistor circuit, the phase difference between the current and voltage is 0, or we can say phi is equal to 0 here, right? And cos 0 is 1. The P average is nothing. P average consumption for pure resistor circuit is VRMS into IRMS, right? Upon multiplied by 1, right? Multiplied by 1. Or we can write it as V naught over root 2, I naught over root 2, right? That's equal to V naught I naught over 2, right? So this is the average power consumption by the pure resistor circuit for the AC source, right? So this was about the what we call as this was the concept about power factor and all, right? Power factor and all, power in AC circuits, average power in AC circuits, and we also discussed about the resonant frequency and quality factor and all, right? So that's it with respect to the alternating currents, right? We have actually touched each and every concept of the AC, right? So we'll stop here today, right? We'll be meeting in the next lecture with the concept of electromagnetic waves, right? So till then, take care and goodbye.